or 9 are on polar coordinates. So first we'll just do the algebra and geometry of polar coordinates today, and then we'll jump into the calculus of polar coordinates tomorrow. So polar coordinates, if you've never seen them before, is thinking about like a radar scope, how that works. You've got some central point here. That central point is known as the pole, hence polar. And then from that central point, we sweep around and around and around and around. Let's see. Tools. There you go. Okay, need a color. And so usually we start right here, kind of like in trigonometry. This would be 0 radians. And remember, in calculus, we always work in radians. Degrees just is not a good unit, but 0 degrees would work too. And then we sweep around counterclockwise. And the way we mark the position of an object with radar is, say this is our object right here. We would want to know how far from our base is it located. That's the radius r. And we would want to know what angle is it from our measuring direction. And so we call that theta. And so this point in polar would be known as r theta. So for example, this point right here, that's pretty close to pi over 4. And let's say I went 2 units out from the center. So that could be the point 2 pi over 4. In a lot of computer systems, to recognize that this is a polar point, not a rectangular point, instead of a comma, they'll put a semicolon in between. And so I will try to remember to do that. Sometimes I'll forget. So usually a semicolon in between indicates polar, not rectangular. Oh, every time I miss the, yeah, I owe you a slice of pizza every time I miss the semicolon. That's a good idea. All right. So, so what we're going to have to first get used to is just, well, how is polar related to rectangular? Because the bottom line is we spent a lot of years playing with rectangular coordinates. We're very used to it, very comfortable with it. Now we have to jump outside of our comfort zone. And so we're going to have to find connections to rectangular to help us feel more comfortable. Now, sometimes that connection to rectangular is kind of pointless and useless. Sometimes it is important. So think about just another analogy. In this country, we use feet and inches, but the rest of the world doesn't. They use the metric system. And we spend way too much time converting between the two systems when we should just be working in metric. So the thing with polar coordinates is some problems are much better off in polar coordinates than in rectangular coordinates. Other problems are better off in rectangular coordinates than polar. So the bottom line is you just want to choose the coordinate system based on with the problem at hand. For example, what the hell do I mean by that? Well, think about a circle. Oops, not circle with a K. There we go. In rectangular coordinates, if we wanted to look at the unit circle, we have to use the Pythagorean theorem to generate it. And we end up with the equation x squared plus y squared equals 1. Okay. You don't usually get to that till like an intermediate algebra class, right? You got to do quite a bit of work before you're ready to deal with that complexity. Now we're all pretty used to it. We're like, that's not complex, that's easy. But you know, in a evolutionary point of view from when you learned algebra, it is pretty complex. In polar coordinates, if we want to generate the unit circle, well, let's see. This point here, this point here, this point here, that point there, how are they related to the pole, the center? Well, aren't they all 1 unit away? So the equation in polar coordinates is simply r equals 1. That's it. So in rectangular coordinates, the unit circle is quite complex. In polar coordinates, it's super simple. Okay. Parabolas, on the other hand, in polar are not so simple. They're better off left in rectangular. But circular stuff, better off in polar. And there's other things we can create in polar coordinates that are super easy, where in rectangular, they're much more complex. Okay. So getting used to it, connections between the two. I'm just going to consider a picture where I'm going to superimpose rectangular and polar on the same picture. So in rectangular coordinates, I have an x-axis and I have a y-axis. And then I pick some point right here, let's say, and we would say, hey, that is the point xy. To get there, I go over x units and I go up perpendicular y units. To describe that same point in polar, I just need to connect it to the pole, which is the origin, and find the radius. And then measure the angle off the positive x-axis. We'll usually use theta to designate that one. So rectangular point x comma y would be the same as the polar point r semicolon theta. Well, what do we know about r, theta, x, and y? Well, I just made a right triangle, correct? And so from basic trigonometry, we know, for example, that the sine of theta is equal to y over r. Oops, that's not an r. All right, opposite over hypotenuse. We know the cosine of theta is equal to x over r. Those are going to be useful. For example, if I rewrite these two, I could say if I multiply the r to the other side, that y equals r times the sine of theta. So if somebody gives me a polar point, I can just take the radius times the sine of the angle, and that gives me the y value instantly. Right? So this relationship allows me to convert from polar to rectangular. And similarly, x would just be the radius times the cosine of theta. So point-wise, this relationship lets me convert from polar to rectangular. Other relationships that are helpful, new page. I know that the tangent of theta, opposite over adjacent, that would be y over x. Rewriting that just a little bit, I could say that theta is equal to the arctangent of y over x. And this would allow me, if somebody gave me the point in rectangular, taking the arctangent of the ratio of the y value over the x value, that gives me the angle, or at least some version of the angle. We'll talk about versions of the angle in a minute. Otherwise, I know the unit circle formula in rectangular coordinates. That's going to be x squared plus y squared equals r squared. And so that tells us that r is either plus or minus the square root of x squared plus y squared. And this is where it gets weird. Because usually when somebody say, hey, what's the radius of that circle? I would say, well, the radius is 1 or 2. Have you ever said before the radius is -1? What does it mean to have a negative radius? So either I just made a mistake writing that down, or maybe it's possible to have a negative radius. Let's give it a try. All right, so often when I'm doing polar coordinates, I'm going to put x and y axes because those are my old bearings. Okay, so I'm going to draw them in anyway when I'm working with polar. And let's suppose I have the point 1 pi over 4, semicolon. So that's polar. And if I label my axes here, let's suppose that's 1 and that's 2, 1, 2, y and x, even though I don't really need them. Whoa, that was weird. My pen freaked out. So let's see, plotting that point, pi over 4, that's kind of right in between the x and the y axis, and then I just go out 1 unit. Well, if I went out here, that would be square root of 2, Pythagorean theorem, so it's got to be closer in. So maybe right about there is the point I want. Oops, come here. Oh, I got you. Oh, no, stop it. Ah, there we go. Get that out of there. So I think that's my point right there. So the way I usually plot a polar point is I first identify what angle I need to head out at, and then from that angle, I then find my radius. Okay, so I picked the direction pi/4 here, and then I went out 1 unit on that. So I could also plot the point 2 pi/4. Same direction. If that's 1 unit there, 2 units would probably be about there somewhere. So this would be my other point. All right, let's plot another one. Switch color maybe. How about the point 1, 5 pi/4? Where is 1, 5 pi/4? So let's see. 1 pi/4 is this direction. 2 pi/4, 3 pi/4, 4 pi/4, 5 pi/4 is out in this direction here. If I go around counting by pi/4, and I want to go out 1 unit, so that would put me about right here. Okay, now we're going to get funky. Can I find the point -1, 5 pi/4? Okay, so I know the direction for 5 pi/4, that's this direction down here. If +1 is to go in this direction, what doesn't negative mean go in the other direction? So that should put me right there. So it turns out this point and this point are the same point. Okay, let's find another point. How about the point 1, 13, oops, that was supposed to be a 3. Let's try again. 13 pi/4. Okay, well, let's see. 2 pi is all the way around, right? So 2 pi would be the same as 8 pi/4. So if this is 8 pi/4, 9, 10, 11, 12, 13 pi/4 puts me right there again. So here's the crazy thing about polar coordinates. There are infinitely many ways to express any particular point. Because we can keep spinning around, we could also spin in a negative direction. Like suppose we wanted to find the point 1, -3 pi/4. Well, this would be negative pi/4, 2 pi/4, -3 pi/4, puts me at that same darn point again. So you could spin in a positive direction. You can spin more than once. You can have a negative radius. So for any particular point, there's infinitely many ways to represent it in polar. There's usually a simplest one. The simplest one will have an angle between 0 and 0 and 2 pi, and they'll have a positive radius. But there are other ways to represent it. Okay? So that gets kind of wild. If anyone gives me a polar point, I can convert it to rectangular, or vice versa. If I get a rectangular point, I can convert to polar. So let's do a couple conversions, and then we'll try to graph something. So suppose earlier we had the point 1 pi/4 in polar. I want to convert that to rectangular. Usually pictures are my best friend, so I would make a quick sketch of that picture. So pi/4 is right through here, and then 1 unit out. Let's see if that's 1 for x and 1 for y, then that would be about 1 for the radius. So that's my point right there. And I want to identify its x value and its y value. And to do that, I know basic trigonometry. So the x value is going to be the radius times the sine of the angle, and the y value is the radius times the cosine. Oh, I got those backwards, sorry. Oops, I missed. missed again. Gotcha. All right, there's my sine, cosine of theta. So in this particular case, my x value is going to be 1 times the cosine of pi over 4. Cosine of pi over 4 is square root of 2 over 2. Or if you prefer 1 over square root of 2, y is the same thing. Oops. So now I know rectangular, this is square root of 2 over 2, comma, square root of 2 over 2. Oops, sorry about that. Thought you were off. Suppose I had a point in, let's see, that was what? Polar, let's go rectangular. Suppose I had the point 2, 3 in rectangular. And we want to convert to polar. I think it's always a good idea to draw a picture. So here, roughly, is my point. And I need to find its radius and the angle. And the radius, that's just Pythagorean theorem. So I know x squared plus y squared is equal to r squared. So what does that give us? 4 and 9 on a good day is 13. So I would like to choose the positive version of that, positive square root of 13. Somewhere between 3 and 4 approximately. As far as the angle, I know the opposite side here and I know the adjacent side here. And I know the tangent of the angle has to be in ratio of 3 to 2. And so my angle must be the arc tangent of 3/2. And I'm going to whip out my calculator to see if I get a reasonable answer. So I'm going to use Google for now. So I want the arc tangent of 3/2, and most computers give radian answers. So Google says that's about 9.83 radians. Usually we don't write units if it's radians, but I'm just going to put it for now. And then square root of 13, what is that about? So I want to see, does this seem like a reasonable measurement? SQRT of 13, and Google says that is about 3.606. If I went, I don't need to go that far, but I guess I will. So that's approximately, so let's see, pi over 3, pi is about 3. 3 over 3 is about 1. So pi over 3, would you agree, is in the vicinity of this angle right here? Right? It's bigger than pi over 4 and smaller than pi over 2. Is this approximately equal to, oops, I put that in the wrong spot. That should be 0.9. And my eraser is missing. There you are. 0.983 is what it should have been. Yeah, so that's pretty close to in the vicinity of pi over 3. So the angle looks right. Does it seem to make sense that this line, the hypotenuse, should be greater than 3? Yeah, it's the hypotenuse. It's the biggest side. It's got to be bigger than the biggest leg. So those answers seem reasonable. Let's see. As far as doing polar graphing stuff, TI can do polar graphing. There's a video on it on the website. Desmos does some good polar graphing, and so does GeoGebra. So I'm going to take a look at those two right now. And I've played with them each a little bit, but not a lot. So this is going to be a fun experiment. So we just had the point 2, 3. And in GeoGebra, if I type the point 3.6ish, is that what we had? Semicolon 0.98ish. That should put me in roughly the same place here. So notice A and B are virtually on top of each other. So Google did interpret the semicolon. Notice, oh, it even converted it to 56.15 degrees, which is a little annoying, but that seems reasonable, doesn't it? Okay. Let's see what Desmos can do. Can we plot points in Desmos? 2, 3. Oh yeah, look at that. And then can we do 3.6 semicolon 0.98? Can you do that, Desmos? Oh, I didn't like it. Darn it. Okay. So Desmos doesn't seem to like plotting points in polar. Bummer. But GeoGebra does. Yeah, it could be that I got the format wrong. So let's see, do they have a help here? Help, search, polar points. What? Oh no, that's a feedback box. Isn't there a search here somewhere? Desmos user guide, help center. Let's try the help center. Search, polar. I think I searched for this earlier and I didn't find anything. Convert to table, graphing the tangent, scatter plots, polar coordinate. Tracing a curve, polar graphing. Now, currently graphing polar coordinates isn't supported. That was 2 years ago. Okay, so I'm pretty sure Desmos can't plot polar points, but I'll do some more research on that. Desmos can graph in polar. GeoGebra can't very easily. There's like a 15-step process to do a polar plot in GeoGebra. It's way easier in Desmos. Desmos can't plot polar points though, which is kind of weird. So there is no best tool, unfortunately. But for example, here in Desmos, if I type y equals x squared, it says, hey, that's a parabola, right? I can do that. Check this out. If I type r equals 1, Desmos says, oh, you mean polar? So Desmos does do polar right away. Okay, so we're going to play around with doing some polar graphs next. Okay, so Desmos does some things good, GeoGebra does other things good. As far as plotting polar points, you got those polar grids I handed out. That's plenty good enough. We're not going to do a heck of a lot with that, except when it comes to trying to do some graphing, but most of the graphing we'll do with technology, except for right now. We're going to try and take a look at a graph. So avoid technology for a moment, please. We are going to try and look at r equals the, let's do the cosine of theta. Now, wipe from your mind the wave that you know in rectangular coordinates, because we are no longer in rectangular coordinate land. We are in spinning around polar land. So this is going to be different. A weird thing about polar coordinates is when we state points, we state r first, and then we state theta. But r here is the dependent variable. Rectangular is the other way around, right? X is independent, y is dependent. Here, r is dependent and theta is independent. So it's kind of a little backwards the way we write the point. What that means is when I make my table, I like to write the independent variable first, because then I have to calculate the dependent variable. Even though when we state points, we write them the other way. Just a weirdness we got to contend with. All right, so let's do some calculations together. If theta is 0, what is the cosine of 0? 1? Yeah, on a good day it is 1. So r is 1 if theta is 0. Next fun angle we choose is usually like pi over 6. Cosine of pi over 6. On a good day, I'm pretty sure it's the square root of 3 over 2. Square root of 3 over 2 is approximately 0.8-ish. Is that right? No, it's got to be, wait. Square root of 3 is going to be 1 point something. I think it's 0.8-ish. I'm guessing 0.887. 0.886? 0.866. Oh, right numbers, wrong order. Okay. So 0. Let's go 0.89 then, 2 decimal places. Okay. Pi over 4. What's that? 0.7-ish? Or 0.87? Oh, 0.866. Right. I still had that other 8 stuck in my head in the wrong spot. Okay. Okay. 0.87? Okay, thank you very much. All right, so pi over 4, square root of 2 over 2, which I think is 0.7-ish. Pi over 3 is popular next. Pretty sure that's 1/2 or 0.5. Pi over 2, 0. All right, whip out your polar paper. Let's plot this and see what happens. Let me get a piece of polar paper. Let's see, where's my home page? Polar paper. And we'll grab a screenshot of that, and I will graph with you. New page. Screenshot. All right, so I made this paper so there were 10 concentric circles so that we could go by tenths maybe. So, ooh, did that get distorted? Ah, darn it. It's distorted, it's right on that screen and wrong on this screen. So the people on the internet are seeing it right, but you guys aren't. I'll fix that another day. All right, so if I say that this is one way out here, then that means each ring is going out by 1/10. Okay, so then let's see, what was my first angle, pi over 6? That would be this angle right here. And we needed to go, what, 0.87-ish? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we're like right here-ish. Okay. And then pi over 4 would be this one right here. And we're supposed to be 0.7-ish there. So that's 0.7-ish, should be right about there. And then 1/2, 1, 2, 3, 4, 5 should put me right here. And then 0 puts me right there. Ooh, interesting. What could that be? Let's keep going. We need more points. What do you think? It might be a circle? Clint's hypothesizing it's a circle. Let's see. Okay, so I'm going to do some more points over here on the side. Theta and R. What's next? 2 pi over 3 is next, I think, after pi over 2. And at 2 pi over 3, I believe we get 1/2 again. And then 1 pi over 4, 2 pi over 4, 3 pi over 4 is next. Notice I also gave you a grid that has all the pi over whatever's on there. For those of you out on the internet, let's get that picture up for you. I think I have it listed here somewhere. Ah, yeah, this is a lovely picture right there. So I printed this out and handed it to the class. I will share it with y'all here to add a link. Polar angle scale. Oh, I can't spell angle. There we go. All right, so keep plotting some points for me there. After, what comes next? 5 pi over 6. And then, no, that's wrong. Is it? Yeah, because then pi comes next. Yeah, 5 pi over 6 would be the next regular angle. Let's link out to that picture. What? No. Ah, there you are. Okay, so there's another link for y'all. Excellent. All right, where's my paper? Okay, so 3 pi over 4, that's also square root of 2 over 2, which is about 0.7. Oh no, I lied. Cosine turns negative at this point, doesn't it? Negative x values, that's negative 1/2. Negative square root of 2 over 2. At 5 pi over 6, cosine sweeps over into the second quadrant, x value is negative, so that's going to be negative square root of 3 over 2. And then at pi, cosine is negative 1, right? Yeah, negative 1. So negative radiuses. Oh my gosh. All right, what do we do with negative radiuses? Well, this angle right here is 2 pi over 3. Normally, I'd be heading out in that direction from the pole. The negative radius says go back through there. Negative 1/2. 1, 2, 3, 4, 5. That should put me right about here. And then, let's see, this should be 3 pi over 4 right there. And I got to go negative 0.7. So that would be coming out this side over here. 9, 8, that would be around right there. This right here is 5 pi over 6. And I have to go negative 0.87-ish, about right here. And then finally, I get back to where I started. If we trace this out, we could put some points in between just to double check, but this looks to me like a circle. With a diameter of 1. So that means the circle would have a radius of 1/2. If it is indeed a circle, I don't know yet. And what's the center appear to be in rectangular coordinates? It looks like it's probably going to be between 0 and 1, which would put it at 1/2. 1, 2, 3, 4, 5. So that should be the center of the circle. If it is a circle. Oh, is it indeed 1/2 up to the top there? It may be. Let's think about this for a second. Let's see, what was the equation we started with? R equals the cosine of theta. Can we get rid of R and theta here? Turns out we can. Think back to our basic triangle. If that's R and this is theta, this is Y and that is X, true? And R is the square root of X squared plus Y squared, is it not? And let's see, cosine on this triangle, isn't the cosine of theta equal to X over R? So if I have R on one side, on the other side, I could replace the cosine with X over R, couldn't I? But R is really the square root, which I could multiply over to the other side. What happens if you take a square root times a square root? They cancel, right? So that's just going to leave me X squared plus Y squared equals X. Oh, that doesn't look quite like a circle. Isn't it usually X squared plus Y squared equals the radius? Oh, but wait, that's only if the circle is centered at the origin. Is this centered at the origin? Oh, this is getting interesting. All right, check this out. What if we bring the X over to the left? X squared, we would have to subtract it, right? So we would have minus X, if we keep the X's together, plus Y squared equals 0. Do you remember completing the square? Way back, think way back to algebra. Completing the square is where you take a pair of things like that and you identify the coefficient on the X term. That's really a negative 1X, isn't it? So that's what we call B here is negative 1. And then we always find out, well, what is B over 2? Well, that would be negative 1/2, wouldn't it? And then what's the next step of completing the square? Anybody recollect? What do you do with that B over 2? You square it. Excellent. Good idea. So we take that B over 2 and we square it, which gives me positive 1/4. And the theory of completing the square is that if you take the X squared minus X and you throw in the plus 1/4, You've just built a perfect square. That must be the square of x minus 1/2. Well, I can't just throw a 1/4 into the equation, right? I have to balance by adding a 1/4 to the other side. So now I have x minus 1/2 squared plus y squared equals 1/4. Wait, isn't 1/4 a perfect square? It's the square of 1/2 equals 1/2 squared. This is the general form of a circle. The center, according to this equation, if you think way back to your algebra classes, is 1/2, 0, and the radius is 1/2, which is exactly what we just drew on the other page with polar coordinates. Okay, now, remember I talked about metric versus our crazy inches and feet system? We should just be measuring in metric. Converting is a pain in the butt. Would you agree in this instant, converting this beautiful polar equation into this insane rectangular equation was kind of a pain in the butt? It was exciting, it was fun, but I don't really need to do that on a daily basis. But we just did prove based on our knowledge of how. So this is how rectangular and polar are related, that simple triangle right there. We can take a polar equation and rewrite it in rectangular coordinates. Sometimes it's way messier in rectangular. That seems a little messier. I mean, it's kind of not too bad. I've seen worse. I look at this one, I think, oh, that's smooth and soothing and relaxing and nice. Okay. So I mentioned before, sometimes polar is a better scheme for doing a problem. Other times rectangular is a better scheme, right? And unfortunately, it's experience that lets you tell which is the better one to work with. So the homework is going to have some painful problems where you're asked to take a polar equation and convert it into a rectangular equation. To do that, you'll have to mess around with this basic triangle and relationships like this. Try and get rid of all the r's and thetas and be left with only x's and y's. Sometimes you'll be asked to go the other way. Given something rectangular, use this to get rid of the x and y's and replace them with r's and thetas and tangents and sines. Okay, mostly it's just to take things you were familiar with and connect them to the new stuff. It's also to reacquaint yourself with all the trig stuff that might have gotten rusty. Although we did a lot of trig last term, I think all of your trig is pretty darn good. So I'm going to stop here. We are officially out of time for class. I'll do a little bit more of this stuff because undoubtedly you're going to have some homework questions. And tomorrow, though, we will start polar calculus. You'd say, well, how could polar calculus be different? Let me give you a quick snapshot. Sorry, I can't help it. When you think about the calculus that we did before, we did two different things in calculus. We found a rate of change, slope. Slope was based on a change in y and a change in x. Wait a minute. In polar, there is no x and y. Huh. Other thing we did is we found areas. How did we find those areas? Well, we took some y value as a height and delta x as a width, and we added up all those little areas. But wait, in polar, there is no x and y. So what does it mean to do slopes in polar? What does it mean to find areas in polar? Because when you make polar graphs, you're basically sweeping out these angles. And so it turns out areas are sectors of circles instead. So we're going to have to look at area in a new way. It's going to be very exciting. Okay, that's it for today. Please log into My Open Math soon if you haven't already.